In November 2024, close-up photography of the Russian Su-57 T-54 prototype at the Zhuhai Air Show revealed significant manufacturing inconsistencies. The images documented misaligned fuselage panels, exposed screw heads, and rivets that were not flush with the aircraft's skin. These surface irregularities increase the aircraft's radar cross-section, or RCS, a measure of how detectable an object is to radar. American stealth platforms rely on extremely tight manufacturing tolerances to achieve a nearly invisible radar signature. Analysts often use these specific manufacturing gaps to categorize the Su-57 as a failed fifth-generation platform. However, the platform is currently being used to launch Kh-69 cruise missiles in Ukraine, and Moscow has secured new export contracts for the jet in the Middle East. Russian Industry and Trade Minister Anton Alikhanov confirmed these signed international deals in February 2026. Evaluating the strategic threat of the Su-57 requires looking past American stealth standards to examine Russian engineering doctrine and the vulnerabilities in its supply chain. The export variant, the Su-57E, provides a non-Western pathway for nations seeking fifth-generation air power. With an estimated unit cost between $40 and $50 million, the aircraft allows buyers to bypass restrictive U.S. end-user agreements and CAATSA sanctions. CAATSA is a U.S. federal law designed to penalize countries that conduct significant transactions with the Russian defense sector. Deploying these jets to countries like Algeria or Iran introduces low observable strike capabilities that alter regional deterrence in North Africa and the Middle East. By providing an alternative to the American and Israeli F-35 monopoly, the Su-57 functions as a geopolitical lever for Moscow, necessitating a technical evaluation of its design. Russian aerospace doctrine fundamentally prioritizes extreme kinematic dominance and the capacity for heavy internal payloads over absolute all-aspect low observability. This wireframe reveals trade-offs required for large AL-41F1 engines and 3D thrust vectoring nozzles. While increasing rear radar return, this penalty facilitates departure-resistant maneuverability, rapid stall recovery, and Mach 1.3 supercruise. Housing large ordnance internally also required a wider wing body, further compromising stealth. This profile suits Russian combat doctrine, operating the aircraft within a friendly integrated air defense system, or IADS, a networked grid of radars and surface-to-air missiles. The Su-57 is a missile carrier designed for speed, maneuverability, and payload over total radar invisibility. The aircraft's multispectral sensor suite, managed by the Shaw-121 system, compensates for its higher radar signature. This schematic details the N036 BELA radar system, including X-band ASA arrays in the forward cheeks. These side arrays allow flying perpendicular to enemy radar, reducing Doppler signature, while guiding missiles. Additionally, L-band arrays on the wing edges utilize frequencies capable of detecting stealth aircraft. Survivability is enhanced by the 101KS atoll system, featuring ultraviolet missile warning sensors and directional infrared countermeasures, lasers that disrupt the guidance of incoming heat-seeking missiles. Through aggressive radar coverage and infrared tracking, Sukhoi seeks to spot enemies first, effectively neutralizing the advantage of Western stealth platforms. While the aerodynamic design is indigenous, Russia faces a significant challenge in mass-producing the airframe. A November 2025 analysis by RUSI detailed specific vulnerabilities within Sukhoi's production lines. Leaked documents from Russian aerospace company OKBM confirm the industry is heavily dependent on imported CNC machine tools, which are essential for modern aerospace manufacturing. This map illustrates the gray market pipeline for electronics. In 2024, unsanctioned importers routed over $25 million of components through China, Belarus, and Kyrgyzstan. Critical Su-57 systems, like the flight control module and electronic countermeasures, completely depend on these smuggled chips. The Su-57's electronic systems are anchored to Western necroelectronics, creating a bottleneck in Russia's industrial capacity. The domestic manufacturing of Su-57 components reveals a geographic fragility in the Russian aerospace industry. This map plots the manufacturing locations for Sukhoi's suppliers, concentrated in European Russia. This includes the SCIF-M facility in Belgorod, providing 70% of specialized machining tools. These critical nodes set within reach of Ukrainian long-range strike weapons. Expanding secondary sanctions while conducting kinetic strikes on these specific geographic points could disrupt Sukhoi's capacity to maintain its existing fleet or produce replacements. The Su-57 clearly fulfills the requirements of Russian aerospace doctrine, yet the platform remains trapped by industrial bottlenecks. Despite its aerodynamic capabilities, the Russian aerospace forces are receiving only a small number of new airframes annually. Russia's reliance on a fragile gray market supply chain is now the primary constraint on its fifth-generation air power. Until Moscow secures its microelectronic supplies and protects its manufacturing base, the Su-57 will remain a capable but numerically limited boutique fighter in global airspace.